Hi everyone. In this video I'll be going over practice exam 5. I can't guarantee I'll go through every problem because there's kind of a lot of problems in the practice exam, but we'll see what happens. So number 1, it says true or false, all functions have inverses. So it says explain your answer. So false, only functions that are 1-to-1 have inverses. Okay. Moving on to number 2. Complete the following statement regarding logarithms. The value of a logarithm is the power to which the base needs to be raised to equal the argument. Okay. Number 3, if the following function is the following function, an exponential function, explain. So no, this is not. If you look at just a piece of its table, so x, let's do -2 to the x over here. So imagine I chose, I don't know, let's choose just 0, 1, 2, 3, 4, something like this. So plugging in a 0, I'd have -2 to the 0, that'd be a 1. -2 to the first, that'd be -2. -2 all squared, that would be +4. -2 to the third, that would be -8. -2 to the fourth, that would be +16. So if you just imagine graphing some of these, maybe I'll call this 0, 1, 2, 3, and 4. I'll call this 16 up here. So at 0, we have 1. So I'd be right about here. Let me just make that in red. And then at 1, I'm at -2. So I'd be somewhere down here now. At 2, we're at 4. So I'd be right about here. At 3, we're at -8. So I'd be back down there. And then at 4, I'm at 16. So it's really doing something kind of like this, but not really. It's doing essentially that, and that's not exponential. Right? We only see constant increase or decrease with exponentials. Okay, on to number 4. Let's see, we have a bunch of compositions to do here. So we have f and g, and then we're asked to compose f and g in these different ways. So for f composed with g of x, something I've been pointing out is that this is the exact same as f of g of x. So what I'll do for this first one is I'll take g, the rule for g, and I'll plug that into all these locations where we have x in f. So I would have 4 times x minus 5 squared plus 3 times x minus 5 plus 2. Okay, we could simplify this. Let's go ahead and do that. So I'll distribute here, and then I'll expand this, and then distribute the 4 also eventually. So we would have 4x squared minus 10x plus 25. I'm leaving out some of the minutia just because this would turn into a much too long of a video. Expanding, we get this, and then distributing, we have 4x squared minus 40x plus 100 plus 3x minus 15 plus 2. Combining like terms, looks like 4x squared minus 37x, right? These combine to make a negative 37. And then 100 minus 15 is 85, 85 plus 2, so I'd have plus 87. What about going the other way? So g of f, this would be the same as g of f of x. So for this one, I'm going to take this rule and plug it in over here. So I would have, instead of x minus 5, I'll have 4x squared plus 3x plus 2 minus 5. So that would be the same as 4x squared plus 3x minus 3 in simplified form. F composed with f of x. So for f composed with f of x, I'm taking f and I'm plugging it into itself. Right? So this would be the same as f composed with f of x. So I'll have, I'm not, by the way, going to simplify this. Some of these are just a little bit cumbersome to do in this video. So what I'll do is just plug it into itself and I'll just leave it there. So I'll have 4 times 4x squared plus 3x plus 2 squared. Then I need to plug itself into the next place where x appears, which is here. And then I still have plus 2 at the end. Okay. Number 4, it says g of 7. So this would be the exact same as taking g of 7 like this. So what I can do is first find g of 7. So g of 7, if I go back up here, here's g. So g of 7 would be 7 minus 5, in other words, 2. So g of 7 equals g of 2. G of 2, again, looking at g, here it is. So take 2 minus 5. So we get negative 3. All right, here's number 4. Moving on, here's number 5. I'll just do a couple of these, and then of course you'll see the rest in a document attached near the video. So it says find the inverse of each function for which an inverse exists. If an inverse does not exist, simply say not 1-to-1. All right. For this one, this is 1-to-1. It would look something like this. Oops. So if you imagine like a horizontal line test anywhere, it'll just hit once. So an inverse does exist. So what I'll do is write y equals x cubed minus 4. That's step 1. Then we switch x and y, just literally as they sit. And now I want to solve for y. So I'll add 4, I get x plus 4 equals y cubed, and then take the cube root. So we have the cube root of x plus 4 equals y. And the final step is just to rewrite y as f inverse. So cube root of x plus 4 equals f inverse of x. Okay. The next one, not one-to-one. Right, that parabola, just this parabola with vertex 0, 0, opening up, this would not pass the horizontal line test. So no inverse would exist. Okay, this one, this would be one-to-one. If you imagine its graph, you have this slope of -1 going right through the origin, so we would have this horizontal line test be passed. So step 1 is to rewrite this as y equals -x. Step 2 is to literally switch them. Step 3 is to solve for y. So we get -x equals y. And then the last step is to rewrite this as f inverse. That's only if this original function is f. On the next one, if we have an inverse, I'll call it h inverse. So I'd have f inverse of x equals -x. So it's actually its own inverse, ironically. All right. One such as this. If you imagine the graph, sometimes kind of difficult to do, but you would have this vertical asymptote over here. Just checking my own graph for a second. So at 0, we should have, yeah, it should be going this way. Sorry, just gonna mess that up. So let's try that again. So we'll have a vertical asymptote over here, and we'll have this part and this part. So if you imagine some horizontal line, it would just hit once. So an inverse does exist. So I'll rewrite this as y equals 1 over x plus 3. Then literally switching x and y, so x equals 1 over y plus 3. Now solving for y. So I can kind of cross multiply if I wish. Right, and I don't know if I wish to do that. So one thing I can do, if I have x over 1 here and 1 over y plus 3 here, I can say 1 over x equals y plus 3. I could just basically flip both sides, inverting both sides, and then subtract 3. So we'll have 1 over x minus 3 equals y, and then I call this h inverse. So 1 over x minus 3 equals h inverse of x. I'll leave this one undone. This one too. Let's go on to number 6. So number 6 says graph the functions on the same plot. All right, so something you can do is just keep using the point plotting method. So if I choose like -2, -1, 0, 1, and 2, this is for f, the exponential. Plug in -2, you'll get 1/9. Plug in -1, you'll get 1/3. Plug in 0, we get 1. Plug in 1, we get 3. Plug in 2, we get 9. So now you can go ahead and plot these. So at -2, we're at 1/9. -1, we're at 1/3. And so on. Okay, there's that one. Something about these functions, if you compose them, so if you find f of g of x, you would have 3 raised to the log base 3 of x, and that's actually just x. If you compose the other way, if you do g of f of x, you'd have log base 3 of 3 to the x, and that's also just x. So actually f and g are inverses. So what that means is to get a table for g, all I would need to do is actually flip f's table. So I could say 1/9, -2, 1/3, -1, 1, 0, 3, 1, 9, 2. And that's only if these are inverses. Okay, can you do that? So I can now plot these. So 1/9, -2, 1/3, -1, 1, 0, 3, 1, 9, 2. Okay. There's that one. Moving on. I'll leave this one undone, but check out the key. All right, let's go on to solving some equations. Here are some exponential equations. We've had a couple different ways of doing these. So for this one, what we want to attempt to do, and it just says solve, so really you have your choice of how you want to do this, but something I'm noticing is that we have a 4 and a 64. So 2 to the 6th, if you check that on your calculator, is 64. And then, of course, 2 squared is 4. I don't really need to show you that, but there that is. So what you can do is change both of these bases. I can say that 4 is the same as 2 squared, and then I'll raise that to x squared plus 2. And then 64, I'll just rewrite that as 2 to the 6th. Powers to powers multiply, so I'd have 2 raised to 2 times x squared plus 2 equals 2 to the 6th. Once you have the bases the same, all that needs to happen is you need to set the powers equal. So I'll have that 2 times x squared plus 2 needs to equal 6. Divide by 2. So we get x squared plus 2 equals 3, and then solve for x. So it looks like plus and minus 1 would work. Again, check out the key for this one. I'll go ahead and try this one though, I guess. Part 3. So 1/36, 6 to the 1 minus 2x. This would be the same as 6 to the -2. So as soon as you have, again, the bases the same, I can set 1 minus 2x equal to -2 and solve for x. So maybe I'll add 2x and subtract 2. So -1 equals 2x, divide by 2. So it looks like -1/2. Remember, you can always check your work. So there was a little bit of a doubt going off in my mind, so I could just say, okay, let's see. 6 raised to the 1 minus 2 times -1/2. Let's see, yeah, this is not correct. Did I type this incorrectly? let's see, was there a mistake made? So right here, I added over 2x, and then I should have added 2. So good, I caught that within the video. So this should have been adding 2, so scratch that. So from here, it should be 3 equals 2x. And then divide by 2. So it looks like 3/2 maybe now equals x. I'll go back over here to the calculator. Let's replace negative 1/2 with positive 3/2. Quite different. 1/36. Okay, good. That's what we were trying to get. All right, so on to some of these compound interest problems. So Anne invested $1,000 in a savings account. If the interest rate is 3.8%, how much will be in the account in 15 years by each of the following methods of compounding? So for compounded daily, we're going to be using the amount equals the principal times 1 plus r over n raised to the n times t. For that, and we're going to have that p is the 1,000. We're going to have that r is that interest rate that was quoted, 3.8. And it is important that you use the percent. N, this says compounded daily. N is always a measure of how many compounding periods are in 1 year. So I'd have n equals 365 for a typical year. T would be this 15 years that was mentioned. So her amount would be 1,000 times 1 plus 3.8% over 365 raised to the 365 times 15. And I'm going to round to the nearest penny for all of these. It should have said that really. So 1,000 times 1 plus 3.8% over 365 raised to the 365 times 15. All right, so that amount. So about equals 1,768.21. All right, so every other week, compounded every other week. So still using this, still going to be using this. The only time it changes is when you are continuously compounding. We have that other formula for that. So every other week, still P is 1,000, right? Everything else is still the same. Except N has changed. There are roughly 52 weeks in the year. So if you're counting how many every other weeks there would be about 26. So I would have the amount equals 1,000 times 1 plus 3.8% over 26 raised to the 26 times 15. So if it's still in your calculator, you can just press left, change these 365s to 26s. So I'm getting about 1767.53. Compounded continuously, this is where we switch formulas. This is where the amount is equal to P times E raised to the R times T. So still we have P of 1,000. Here we have the interest rate still as 3.8%. T is still 15 years, right? And E is this known number. A equals 1,000 times E raised to the 3.8% times 15. So 1,000 times, and then on this calculator you can access e to the whatever by going shift ln, and then 3.8% times 15. So about this amount. So about 1768.27. All right, moving on. I'm going on to number 11, actually. So it says, Katie is a researcher at the Center for Disease Control and Prevention. She is studying the growth of bacteria. She starts her experiment with 1,000 bacteria, which grow at a rate of 10% per hour. How many bacteria will she find after 72 hours? So we should see that the amount depends on the initial amount times e raised to the kt sometimes, or sometimes rt. Either way. So what we're going to have is that the initial amount is this 1,000. We have this growth rate, r equals 10%. And then we're wondering after 72 hours. Right, so the amount after 72 hours would be, well, it depends on the initial amount, times e raised to the 10% times 72 hours. So interestingly, I don't have to change much from the previous one, even though I'm talking about a totally different problem. So I can just say 10% times, that wasn't the times, was it? Times 72. So about this many bacteria after 72 hours. I'm going to round down because that last one is still being formed, so I'm just going to cut it off right here. So 1,339,430. All right, moving on. Write each equation in its equivalent exponential form. So yeah, we had this connection that said if you have y equals log base b of x, then that's completely the same as b to the y equals x. So this is the exponential way of saying this. This is the logarithmic way. So we're attempting to go from left to right here for number 12. So if this was the base, well, then the base gets raised to whatever the logarithm was equal to. So I'd have 3 to the 4th equals x. That's all that this problem is wanting. I'd have n cubed equals 10. I'd have 2 to the 5th equals x. I'd have p to the 4th equals 3. Right? Just going the reverse direction, I'd have log base 2 of x equals 7. All right, now we're just going from right to left. Log base m of 11 equals 4. And so on. On to number 14. All right, it says the Los Angeles area experiences many earthquakes. In 1994, the Northridge earthquake measured a magnitude of 6.7 on the Richter scale. In 2014, Los Angeles also experienced an earthquake which measured 5.1 on the Richter scale. Compare the intensities of the two earthquakes. So yeah, we have R equals log base 10 of the intensity. Kind of a simple model. So for the 1994 one, we would have that 6.7 equals log of whatever intensity we saw there in 1994. For the 2014 one, I would have 5.1 equals log of the intensity of that earthquake. So solving for I on each, and each, as I said, both have a base 10. So I could rewrite these into exponential form. I'll do that over here by going 10 to the 6.7 equals the intensity of the 1994 one. And then 10 to the 5.1 equals the intensity of the 2014 one. So the comparison comes from taking 10 to the 6.7 divided by 10 to the 5.1. Let's see what this is. So this is about equal to, I'll just say, about 40, just round up. So the 1994, sorry about that, quake was about 40 times the intensity of the 2014 one. Okay, I'm skipping pages. Please do read the key if you're interested. I'll move on to number 17, expanding. So we have a few properties that we've learned. I'll write them up here real quick. So log base b, if you have a product, m times n, you can split that up into a sum. If you have a quotient, you can split that up into a difference. And then finally we have this one where if you have a power, so if you have log base b of m raised to the p, that you can bring that p out front as a product. Okay, so those three, 1, 2, 3 are kind of the main ones that we're going to use to simplify these or expand and condense as needed. So the first thing I'm going to do is split this up into a sum. So log base b of x to the 5th plus log base b of the square root of y. Right, so I can apply this one. Since I have a product, I went to a sum since we're expanding. The square root, same as the power of 1/2. And also I can bring out this 5. So I'll bring out the 1/2 over here and the 5. So we get 5 log base b of x plus 1/2 log base b of y. Let's go on to part 3. So I have an ln, I have this kind of multifactorial product here. So something I can do is split up this across these two products. So I can say ln of 2 plus ln of x plus ln of e to the root 3 times x. Right, so I have kind of a triple product, so I'm basically extending this, just imagining that there were like a Q here. Right, I would just have another round of that rule taking place. Over here, we get a simplification actually. So I'd have ln of 2 plus ln of x plus root 3 times x. And that would be the fully expanded form of that. Skipping down to part 5. So this is a quotient property first. So that division, I'll rewrite that first. So log base 3, cube root of x squared minus log base 3 of 27y to the fourth. I have a power rule here, and then I have a product rule here. So I can bring out, I'm basically thinking of this as x to the 2/3. Remember the cube root of something squared? Same as the 2/3 power. So I can bring out that 2/3. Right? Here, I need to split this up across this multiply. So I'll go minus parentheses log base 3 of 27 plus log base 3 of y to the fourth. Now this negative needs to distribute here. So I have 2/3 log base 3 of x minus, well, log base 3 of 27, that simplifies, right? Log base 3 of 27, that's the number 3. So I'll just make that simplification. So minus 3, and then minus log base 3 of y to the fourth. And then just one more thing, I need to bring out that 4. So 2/3 log base 3 of x minus 3 minus 4 log base 3 of y. All right, so what about condensing? So yeah, we can use those same properties to go the reverse direction, this condensing direction. So if I have a sum already and the bases are equal, then I can bring these together and say log base 6 of 4 times 9. In other words, log base 6 of 36. In other words, the number 2. Right? Remember, the value of a logarithm is the power that you put on the base to equal the argument. So the value of this logarithm, in other words, what number this is, right, this 2, is the number I put on the base. So it's the number I put on this base as a power to make a 36. So 6 squared is 36, so that's why this is the number 2. Just as a way of verifying, you can plug this in to the calculator. Okay. Let's do a slightly more complicated one. I'll go down here to L. So first on L, what I need to do is actually bring up these as powers. So I can use that property first. So I'll go log base 6 of x to the 1/3. You can write that as a cube root if you want. Minus log base 6 of 4 squared, so I'll just write 16, right? That 2 is coming as a power on the 4. Then minus log base 6 of z squared. Okay, so now I have a bunch of log base 6 logarithms, so I can go ahead and further condense. So I'll use the quotient property. So I can say log base 6 of x to the 1/3 over 16 minus log base 6 of z squared. And then I can do that again, right? This z squared will come down here as well. So log base 6 of x to the 1/3 over 16 times z squared. This would be it. All right, let's solve a logarithmic equation. It says round your answers to 3 decimal places. All right, so what I want to do is use those same properties and go ahead and condense actually the left-hand side. So I'll say log base 3 of x plus 1 times, since it was plus, it turns into multiply, x plus 2 equals 2. And then I can do this kind of switcho-changeo thing and say, well, here's the logarithmic way of saying this thing. Let's write it as an exponential. So 3 squared must equal x plus 1 times x plus 2. So I need to solve this now for x. So foiling, we get x squared plus 3x plus 2. Subtract 9, I want to get my 0 and solve this quadratic by some method. All right, so it looks like this thing factors. Does it factor, or do I take that back? It looks like I take that back. So let's use the quadratic formula. So a equals 1, b equals 3, c equals -7. So I'd have x equals the opposite of b, plus and minus the square root of b squared minus 4 times 1 times -7, all over 2 times 1. See what numbers these are. Okay, they're weird numbers. So I'm getting x plus as -3 plus, oops, sorry about that. So -3 plus root 37 over 2. And then x minus, go back and change that. I'll rewrite it actually as -3 minus root 37 over 2. This is about equal to -4.5, by the way. And just for our information, I'm going to see what the decimal approximation is of the other one. It's about 1.5. Okay, so one of these is no good. So if I try this one, it actually won't work. And I'll leave that to you. But if you try this one, it actually won't work. This is the only one that works. It's said to round to 3 decimal places. So I'll actually take this out to 541. I'll just cross this one off. Okay, moving on. All right, this one says a car is purchased and begins to decrease in value according to this function p, where p represents the percentage of the original price that the car should be sold for at time x, where x is the number of years after purchase. Okay, so for what percent of the original price can the car sell for after 3 years? So p of 3. So 100 minus 30 times log 3 squared plus 1. Can plug that in. So 100 minus 30 times log of 3 squared plus 1. 70%. So 70% of its original value at 3 years. For what percent of the original price can the car sell after 10 years? Round your answer to 2 decimal places. So p of 10, so 100 minus 30 times log of 10 squared plus 1. Okay, so round your answer to 2 decimal places. So this would be about 39.87%. Okay, finally on to part 2. There were 2 part 1s for some reason. How long does the car take to depreciate down to 25% of its original price? round your answer to 2 decimals. So instead of plugging in on the x, we're now plugging in for p of x. So if I force the percentage to be 25, what number of years leads to that, basically, is the question. Okay, so we have to solve this logarithmic equation for x. So I'll go ahead and subtract 100. We get negative 75 equals negative 30 log x squared plus 1. Divide by negative 30. So we get 5/2 equals log of x squared plus 1. So by the way, if it's not written and it says log and not ln, then this is a base 10 logarithm. So if I convert this to exponential, I would say 10 to the 5/2 equals x squared plus 1. Right? Solving for x, I'll go ahead and subtract 1. So 10 to the 5/2 minus 1 equals x squared. Take the square root. I'm not going to think about negative time, so I'll just cross out that negative. It says round to 2 decimal places, by the way. So square root, 10 raised to the 5/2 minus 1. It's about 17.75 years. So that's how long it takes the car to get down to 25% of its original value. Let's see, we have a mixture. So it's actually a typo to say solve each logarithmic equation. So these first two are logarithmic, but these next two are actually exponential. So I'll just solve one of each. So what we can do is rewrite this into exponential. So 2 to the 5th equals 8 minus 6x. So I'll subtract 8. So 32 minus 8 is 24. And then divide by negative 6. So negative 4 equals x, and then you do want to check these. So log base 2 of 8 minus 6 times negative 4. I'm hoping for a 5. That does happen. But make sure to check these ones, because you could get answers that are actually not correct. Let's go down to part 3. This is actually an exponential equation. So what I want to do is get the exponential piece alone. So I'll have 29 thirds equals e to the 2x. And now apply a logarithm. So I'm going to match the base. So I'll choose an ln. 29 thirds equals natural log of e to the 2x. Cancel these away. ln of 29 thirds equals 2x. Divide by 2. It says leave all answers in exact form. So my answer would be ln of 29 thirds over 2. All right, let's see what's next. All right, so these last two. So it says the world population P of t in billions, t years after 2000, can be approximated by this function. How many years until the world population reaches 10 billion? Round to 4 decimal places. Okay, so P is measured in billions. So if I'm wondering about 10 billion, I'm just going to plug in 10 there. So I'll have 10 equals 4.553 times 1.014 raised to the t. I have an exponential equation here. That means likely I'm going to need the use of a logarithm eventually to solve this. So I want to get this exponential piece alone. So for that reason, I'll divide by 4.553. Don't subtract, right? That's attached through multiply. So we're dividing that away. So we get 10 over 4.553 equals 1.014 raised to the t. Apply a logarithm. What I'm going to do is choose a logarithm with a base of 1.014. So I'll have log of base 1.014 applied to both sides. So the purpose of that is on the right, these cancel, and now we're just left with t is what we were after anyways. So I'm getting that t would equal log of 1.014 of 10 over 4.553, but it said round to 4 decimal places. So I'll type that in and then round. So it looks like 4 decimal places. I'm going to stop right here. So that's going to change that to a 4. So t equals about 56.5924 years after 2000. Find the doubling time. So the doubling time doesn't mean how long it takes 10 billion to double. It means the initial amount. How long does it take that to double? So I'd have over here, instead of 10, I'd have 2 times 4.553 equals 4.553 times 1.014 raised to the t. So I can cancel these away since they're on the same side. So I just have 2 equals 1.014 raised to the t. And then choose another logarithm. I can use the same base. So log base 1.014 of 2 equals log of 1.014 of 1.014 raised to the t. So these cancel. And this would be our amount of time. So t would equal log of 1.014 of 2, and it says round to the nearest year. So type that in. So it's about 50 years. And that'd be after 2000. Okay, one more. So 23, it says the amount spent each year by the U.S. government for health insurance on children in low-income families can be estimated by this function. This is a logarithmic function, by the way, where h of t is in billions of dollars and t is the number of years since or after 1998. It says how much was spent on health insurance for children of low-income families in 2007. Round to 4 decimal places. So 2007 is 9 years after 1998. So I'd have t equals 9. So h of 9 is what we're looking for this one. So 2.6 times ln of 9. And this is in billions, by the way, right? H is in billions. So 2.6 times ln of 9. This would be, I guess, round to 4 decimal places. So this is about equal to 5.7128 billion dollars. In what year will 20 billion be spent on health insurance for low-income children? So instead of plugging in over here, now we're plugging in for h. So I'd have 20 equals 2.6 times ln of t. Trying to solve this for t. So I'll divide by 2.6. So 20 over 2.6 equals ln of t. And ln of t, or ln of anything, this is a log base e. So really there's a base e there. So really you'd need to, if you want to switch it to exponential, you'd say e to the 20 over 2.6 equals t. So in what year? So this is the time, but we need to figure out in what year that is. Okay, so this is a long time from now. So this would be, it's kind of a ridiculous question. So this is 2,191 years after the year 2000. So this is about the year 4,191. Okay. Good luck on the exam, you guys. Talk to you soon.